1, 2, 3, 4 here on this paradise substituted, and then here's 5, and then there's a bromine. Just there, that alone, we should know what the structure is. Just looking at degree of unsaturation and IR, but let's confirm what the structure is. So hopefully you already can see what the structure should be. All right, so looking at our proton NMR now, 5.1 is the lowest thing that we have. 5.1, that usually we have something really far upfield, right? We have things at like 1.7, 1.9, 0.9. We have nothing there. We just have 5.1. So everything here is very deshielded. So a lot of things pulling away electron density from one another. But we see that this is a broad singlet. So we know it has to be an OH. And we label that as 5.1. I can't see the things beside it because it is a proton that can come off and go back on. It's very acidic. All right, 6.7. Look at your sheet. What would the range be for 6.7? So this should be in the range of the benzene ring, right? Aromatic. You see that? Aromatic region. And so these hydrogens have to be aromatic hydrogens if they're anywhere between 6 and 9.5, so 6.7. So we're going to draw a benzene ring, not a CH2, right? We're not going to do this. Why are we not going to do this? Because we see this is aromatic, we're not going to do this kind of thing. We're going to do this. We're going to draw a benzene ring. And with that benzene ring, yes, there are 2 hydrogens, but those 2 hydrogens have to be symmetrical to one another. It's not a CH2, right? There's no way for us to have 2 hydrogens on one of these carbons. Let me draw in these double bonds so you can see. Each of those carbons can only have one thing bonded to them. So this has to be 6.7, and this has to be 6.7 based on symmetry. Now they are 6.7, so it's aromatic, 2 hydrogens. So based on symmetry, they are 2 hydrogens symmetrical to one another, but they are doublets, meaning that they have 1 hydrogen neighbor. With that 1 hydrogen neighbor, I drew it there, but we don't actually know that they're right beside, right? We're not sure. So let's make sure. What would tell us for sure where those hydrogens are? 7 Hertz coupling. So 7 Hertz coupling, ortho coupling. So as I've drawn it, yes, that is correct. These 2 hydrogens have 1 hydrogen neighbor. That is ortho. That's our building block piece. We know that 6.7 doesn't have another ortho hydrogen. So I'm going to put this here and I'm going to just put R. There can't be a hydrogen there. R does not equal hydrogen. And then I know that it doesn't have anything meta. Meta coupling would show up here, 1.2 to 3.1. There is no 1.2 to 3.1, so there's nothing meta either. So I know I have some other R group there. All right, now I move on to my next one. 7.3 is still in the aromatic region, right? Our aromatic hydrogens, that's what we're looking at. We also had this benzylic, but we know that there are no hydrogens right beside the double bond because there's nothing down this low, this upfield, 2.2 to 2.5. So we know that everything here has to be on the benzene ring, not something beside the benzene ring. But anyway, so we have 7.3, 2 hydrogens, it's a doublet, but look at this, we're seeing that 7.0 Hertz again. So this has to be 7.3, and this has to be 7.3. Based on symmetry, these 2 have to be symmetrical to one another, We know that this is a symmetrical molecule because this is a paradise substitute. That's what we saw in the last slide. We just saw that it was a paradise substituted benzene ring. So this is enough for us to put the structure together and then assign every one of these carbons and hydrogens in our final structure. So here's our final molecule. Look at our molecular formula. C6, we have 6 hydrogens. H5, we're showing 4 hydrogens. We know one of these needs to be an OH, so I'll just put OH here. And one of these needs to be bromine attached. Now we have assigned all of these atoms here. All right, let's figure out what each of these things are. So our hydrogen of the OH, we know that that's 5.1. And then we have 6.7 and 7.3. Now, remember with the oxygen, remember that this oxygen can be an electron donating group by resonance. So anything close to it is going to be more upfield. Electron density is being donated N by the oxygen. So closest to the oxygen would be 6.7. On both sides of the oxygen, symmetrical. Closest to the bromine, because that's electronegative, right? That's an electronegative atom. So that is an electron withdrawing group by induction. It's going to be something that is more downfield, so 7.3. Now we need to look at our carbons. So for our carbons, we have a quaternary carbon, another quaternary carbon, 113 for this one, 154 for the other. Look at your carbon NMR sheet. So for the alcohol, a carbon that's connected to the alcohol, that's going to be between 50 and 90. But a carbon that's connected to bromine, that's going to be between 20 and 40. So obviously the carbon connected to the oxygen is going to be more downfield here. So this is going to be our 154, that carbon. And this carbon is going to be the 113. Quaternary carbon, no hydrogens on it. Quaternary carbon, no hydrogens on it. And then we have 2 more. We have 117 and 133, but I still have 4 carbons. Why would I only have 2 more peaks? Remember, symmetry. So whatever we assign to be this one has the exact same chemical shift. So what's the chemical shift of the carbons that have the that are beside the OH? Well, remember, yes, the OH can pull away electron density, but it can also donate to these positions. And so 117 would be the chemical shift there. And then these 2 would be the 133. Again, because of that electron withdrawing bromine. So this would be our structure. This compound is called 4-bromophenol, or the common name, para-bromophenol. And we've assigned all the hydrogens, we've assigned all the carbons. We previously showed why we have those J values, so we've answered this entire problem. Questions on this?
I had a question. How can you distinguish, I know you mentioned it before, but how can you just distinguish like when you have 4 pi bonds versus when you have a ring?
So we know that for a benzene ring, there is a ring. So that's 1 on saturation. And then in the benzene ring, we have these 3 double bonds. And so we know that a double bond is a sigma plus pi. So we have 3 pi bonds and 1 ring. Other questions?
Yes. How did you know from just the IR that it was para, the benzene ring?
Because of the 827.
Okay, but
Because
you wouldn't
we
give us like
have
an actual, because that's in the fingerprint region. So you wouldn't give us like you would just give us the number on the exam, or would you
right,
give us
yeah.
like a okay?
No, I
Thank you.
gave you the numbers. Yeah.
Okay.
Because that could be covered up also. Other questions? All right, then let's go on to chapter 16. So basically, chapter 15 and 16 are kind of one. It kind of flows. So we learned some stuff in chapter 15, and now we're going to apply it to stuff we're learning in chapter 16. So basically, we're going to learn how can you synthesize all these molecules? How can you take a benzene ring that has one group on it, and how can you add in another group by further electrophilic aromatic substitution reactions? So we talked about how to do just one, but now we're going to talk about how to do two, three, four, on that benzene ring. What happens there? First, let's look at Jeremiah 33, 2-3. It says, "This is God's message, the God who made earth, who made it livable and lasting, the God who's known everywhere as God. This is what he says to you. He says, 'Call to me and I will answer you.'" He's promising you, "Call to me and I will answer you. I'll tell you marvelous and wondrous things that you could never figure out on your own." So I think that everything that you're learning in this class and also probably in your other classes would count as these marvelous and wondrous things that you could never figure out on your own, but you can figure them out with the help of God. So call out to him. He will answer you. He will reveal things to you that you couldn't figure out on your own. He'll reveal pretty cool things to you, but he's promising this to you. Remember, he's the one that created all this. He made the earth and made it livable and lasting. So he's the one who knows the answers to these questions you have. All right, so for our electrophilic aromatic substitution, we were just talking about how to make it monosubstituted, right? We just were saying we can put one thing onto that benzene ring and we use that one thing to make other things. But now we can do more electrophilic aromatic substitution reactions on that benzene ring. So whatever's on the ring is either going to activate or deactivate the ring. Whatever we put onto the ring, that benzene ring, is going to activate or deactivate it for further reactions. And it's also going to direct where the next group adds on. It's going to do two things. It's going to either activate or deactivate, and it's also going to direct where the next reaction is occurring. So they're showing you here something that we'll learn about more. So this is just a brief introduction. But if we have some kind of a donor, that's going to activate the ring. Something that is an electron donating group, it's going to activate the ring. But if we have an electron withdrawing group, an acceptor, something that accepts electron density, that's going to deactivate the ring. In general, something that activates the rings will direct the reaction to happen ortho or para to it. In general, something that deactivates will direct the reaction to occur meta to it. But let's look at that in more detail. So remember we talked about our Diels-Alder. We said the dienophile should be electron poor and our diene should be electron rich. And so how do we make it electron poor? Electron withdrawing groups. How do we make it electron rich? Electron donating groups. But we still have to keep that same, what's an electron donating group? What's electron withdrawing group? We have to keep that same concept in our mind here when we're talking about the electrophilic aromatic substitution reaction. The reaction is going to work best when we have some kind of electron donating group there because the ring is electron rich. That's going to be the best thing. We want our benzene ring to be electron rich for this EAS reaction. So the rate is going to be fastest when we have something that's an electron donating group. So we know that this is an electron donating group by induction. And so here our ring is electron rich. But why would this be the slowest rate? Well, we have a nitro group, which we know is an electron withdrawing group by resonance. And so this is an electron poor benzene ring. And then in the middle, we just have regular benzene. That works well for the reaction, but if we put on something electron donating, that's going to make the reaction even faster. So remember, we're talking about induction, which goes through the sigma bonds, and resonance, where we are moving around pi bonds. So we have those two concepts, resonance, which is really through sigma bonds, and then, induction, which is through sigma bonds, and resonance, which is where we are moving around pi bonds. All right, so looking at the inductive effects first, we can pull away electron density or we can donate an electron density. But remember here, we're really talking about electronegativity. We're really talking about these polar bonds, polarized groups. So if we have something like 3 fluorines, so if A is a carbon with 3 fluorines, you know those fluorines are pulling electron density toward themselves away from the carbon, but you know they can pull them through neighboring bonds. That is induction. And so you see all these atoms here that are electronegative, so any of our halogens. Here our oxygen is electronegative, nitrogen and oxygens. Here we have all these oxygens. All these groups can pull away electron density by induction. Because they are electronegative atoms, they're pulling electron density through these sigma bonds, making this electron poor. But if we have some kind of a donating group by induction, what would that be? Really just our alkyl groups. So any kind of an alkyl group, those carbons. Why? Because this carbon here is sp2 hybridized, and we said those carbons are electron withdrawing groups, right? We said that if it is sp2 hybridized, we can pull away electron density. And so as we are pulling that electron density, the alkyl group is technically donating an electron density. And so that is what's happening in our electron donating group by induction. So the alkyl groups are electron donating groups by induction. And then we have our CF3, nitrogen, oxygen, halogens. We have our carbonyls, any kind of carbonyl, cyano group, nitro group. This is our sulfonic acid group. All of those we've seen before, and now we're looking at them in this context as electron withdrawing groups. But then resonance effects are more important than inductive effects. We said this before. Resonance is really more important than inductive effects because resonance allows us to get full charges. Inductive effects, we just get partial charges, but resonance allows us to get full positive, full negative. So something that has at least one lone pair on it, the atom directly bonded to the benzene ring, has to have at least one lone pair. So you see one lone pair here on this atom, they're just calling D, which would be whatever is directly bonded. So nitrogen, oxygen, and then the halogens directly bonded to the benzene ring. If there's at least one lone pair on there, then technically this group can donate an electron density by resonance. And so we get these different resonance forms where we can delocalize the negative charge around the ring, and that atom gets a positive charge, a full positive charge when it donated in its electron density. But we allow for our ring to be electron rich, right? This is electron rich. If there's a negative charge here, obviously we have an excess of electron density. So having one of these groups that can donate an electron density by resonance is going to be really nice for the benzene ring. It's going to improve the rate of this electrophilic aromatic substitution reaction. Now look at all these atoms. We have nitrogen, oxygen, and the halogens. That's what we're talking about. So yes, these are all resonance donors. So these are all electron donating groups by resonance. But these groups, we saw them on the previous slide. Where did we see them? Right here. So they are both electron donating groups by resonance and electron withdrawing groups by induction, because they are electronegative atoms. They can do both things. They are resonance donors and also inductive electron withdrawing groups. But for these, what's the difference? Well, our amines and our alkoxy groups, these are going to prefer to be resonance donors, whereas our halogens are going to prefer to be electron withdrawing groups. They're better inductive acceptors. They're more electronegative than nitrogen and oxygen, so they're better at pulling away electron density by induction, whereas nitrogen and oxygen are better at donating in their electron density, so they're better resonance donors. Questions there? All right, then let's look at these groups. So when we have a double or a triple bond, right here, so the atom directly bonded to the benzene ring is involved in a double bond to another atom. It also has to be polarized where there's some partial charge, so partial positive, partial negative here. So where we have this polarized double bond or polarized triple bond directly bonded to the benzene ring, the positive end is bonded to the benzene ring, we can withdraw electron density by resonance. So we can push electron density. The atom that has a partial negative is pulling electron density so that then in one of our resonance forms, it ends up with a full negative, and atom B ends up with a full positive. And so with that full positive, we can pull electron density out of the ring where now we have a positive charge. And so with a positive charge, what's happening there? This is electron poor, right? Positive charge, electron poor ring. And so with this now, we are going to be deactivating our ring. So notice that we saw these before. We saw these groups before, right? The carbonyl, cyano, nitro, sulfonic acid group. We saw them before as inductive electron withdrawing groups, and now we're seeing that they're also resonance and electron withdrawing groups. So these are electron withdrawing groups by both resonance and induction. So we can see how the ring looks. Where's the electron density on the ring? So for a regular benzene ring, we know that we are all of our electron densities delocalized over all those atoms of the ring. So we see that red area nicely over all 6 of the atoms of the ring. Methylbenzene, what's a methyl? An electron donating group by induction. We can see that the ring has a red area. Aniline, nitrogen, hydrogen, right? You should know what aniline is, but this is what's most important. It has that lone pair. So we know that, yeah, this is an electron withdrawing group by induction, but it's an electron donating group by resonance. And that's what's most important here. Look at the ring, high electron density, because that nitrogen is donating in electron density. But for the nitrobenzene, that nitrogen has no lone pair on it. This nitrogen has a double bond to oxygen, a single bond to oxygen. So the nitrogen has a full positive charge. So with that, this is just an electron withdrawing group by induction, because nitrogen is an electronegative atom, and by resonance, because we can pull this electron density over here over to this oxygen. So what did we say? If it's electron rich, the arene there, it's going to have a faster rate. Questions on this? All right, so let's talk about this stuff more in detail. So this is 16-2. So we said when we have an electron donating group, so here, electron donating group by induction, we have toluene here. And so that methyl is donating in by induction. What happens is that the ring is activated. And so with the ring being activated, we have a good reaction that occurs. So we see our ortho, meta, and para products. So for this, we mainly get the ortho and the para product, trace amounts of the meta product. So it doesn't matter what's on the ring, it just matters the properties of it. So because this is electron donating, we're seeing that this is an ortho para director. This group is an ortho para director. So this reaction is regioselective, meaning that it's going to occur in a certain region, right? It prefers to occur in the ortho and the para positions. So methyl is an ortho para director. Why is it an ortho para director? Well, let's look at our rate limiting step. The first step, right, is to attack an electrophile. When we attack an electrophile, we end up with these resonance forms. Look at our resonance forms. We end up with one here that is a tertiary carbocation. So we know that that's going to be most significant because here we have secondary, here we have secondary. If we look at our addition in the para position, again, we get another tertiary carbocation. But if we look at what would happen if we added it to the meta position, secondary, 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 we can't access through these resonance forms a tertiary carbocation. And so the molecule knows that it doesn't want to add into the meta position. It knows that the ortho and the para positions are favored. But between the two, in general, para is going to be the major, and then minor will be the ortho based on sterics, right? Look at this, trying to occupy the same space, this methyl and the bromine. Bromine's large, that methyl's large, trying to occupy the same space. We have larger groups there, obviously, but here there's going to be a little bit of steric, so it's easier for us to have those two groups as far away from each other as possible. All right, so moving on to a group that is an electron withdrawing group by induction. How do I know? It's a CF3 group, those 3 fluorines pulling away electron density. When we have this on the ring, this CF3, it's going to deactivate the ring. So this is deactivated. This reaction is going to be slow. So what we do is we heat up the reaction mixture, delta. That's going to help the reaction to proceed. When the reaction occurs, look at what we get. We mostly get the meta product here. Electron withdrawing groups, in general, are meta directors. Electron withdrawing groups are meta directors. So let's look at why this is true. Why is this a meta director? Well, when we do our first step, we attack our electrophile, look at our different resonance forms. So, okay, we get the exact same resonance forms if it was CH3 as if it was CF3. But now, remember, with this being CF3, electron density is being pulled away. What's happening here? We have electron density being pulled toward the fluorines. That destabilizes this. This is a destabilized cation. If it was a CH3, that methyl could donate an electron density to stabilize by hyperconjugation. Now electron density is being pulled away. This carbon has a positive charge and electron density is being pulled away. That is going to destabilize that cation. So we don't want to do this. We don't want to do this. These are really bad carbocations now. If it's a CF3, because the fluorine is pulling away electron density. If it was a CH3, this would be fine because the methyl could donate in electron density to stabilize that positive charge by hyperconjugation. So the molecule knows avoid ortho and meta, ortho and para, and have the reaction happen here at the meta position where it is less destabilized. Less destabilized. So Our substitution is directed away from the ortho and para positions. Questions on that? All right, so those are our two types of inductive, electron withdrawing and electron donating by induction. Now let's look at some other ortho-para directors. Here we have our nitrogen with a lone pair, one lone pair, and our oxygen with two lone pairs. So aniline and phenol. With aniline and phenol, these are strongly activated benzene rings because these groups are electron donating groups by resonance. The nitrogen, the oxygen, they're going to donate an electron density to the ring, and so the reaction's going to work very well. It actually works so well that we don't need a catalyst. So notice here, there's no FeBr3 or AlBr3, no catalyst needed, and it occurs quickly at all open ortho and para positions. Notice what these products are. We didn't get monosubstitution, right? We don't add just one bromine. We added bromine to all open ortho and para positions. If you don't want the tribromal product, then this isn't good. If you want the tribromal product, then this is great because you get excellent yield. You don't need a catalyst. Your reaction works very quickly because these groups are going to activate the benzene ring for the reaction. Why is this happening here? Well, for the nitrogen, and we know the oxygen would do the same exact thing, we have this lone pair. And so notice after we add in the electrophile, the lone pair on the nitrogen can be moved here where it can. Instead of having a positive charge here, now we can put a positive charge on the nitrogen. So we can make a double bond. So now what is the difference here? Every one of our atoms has an octet. Instead of having this carbon that has a sextet, only 6 electrons around it, we have all octets. And so this is going to be a good resonance form, our best resonance form. We again get another all octet resonance form here if we add it to the para position. And so the ortho and the para positions are activated for the reaction occurring. For our meta, we know that none of those, they're fine. They're secondary carbocations. There's nothing necessarily wrong with them. But if we can make a better resonance form, then the molecule knows it's going to go that direction. Something lower in energy, it knows it wants to make that. So we get 4 resonance forms instead of just 3. More resonance forms, more stable. And we get an all octet form. 4 resonance forms instead of 3, more stable, intermediate. And we get all octets, which we know is a good thing to look for when we are talking about our resonance forms. Questions there? So we know that the oxygen and nitrogen, yeah, by induction, they can pull away electron density, but they are electron donating by resonance. And we can see here them the nitrogen donating in electron density. So the same would be true with phenol. So for this, hold on one second. Sorry, this won't erase. But anyway, for this reaction, if we have aniline, it's going to be very activated. If we have phenol, it's going to be very activated. So we have our phenol, we change it to methoxybenzene. If we have our aniline, we change it to N-phenylacetamide. So we're adding this acetyl group to the nitrogen. What is that acetyl group doing? It's pulling away electron density, right? Partial negative, partial positive. And so we get this resonance form where the nitrogen is pushing electron density into that acetyl group instead of being able to push it into the ring. So we get this resonance form. where we end up with our nitrogen. Now with a, no, this isn't going to work right here. Hold on. Let me draw it over further. Single bond still to hydrogen. Now double bond to this carbon, where now the oxygen has a negative charge. So we're pulling out our electron density. Instead of just having that lone pair available to donate into the benzene ring, now the lone pair can either go into the benzene ring by resonance or can go into the acetyl group by resonance. And so that pulls out some of that electron density, so it reduces the activation of the ring. Reduces the activation of the ring. Something similar is happening with the methoxybenzene. It's just deactivating it by making it into an ether rather than an alcohol. But it's not like a resonance thing happening there. But anyway, when we do this reaction, notice what we get. Now we get the monosubstituted product. So we can get mostly the para disubstituted products rather than having that nitro group add to both of those ortho positions and the para position. We are only going to add it to just the ortho or just the para position. So in order to do the monosubstitution, we have to change our phenol and our aniline into other compounds so that we can do just this monosubstitution. Questions on that? All right, so then we have here an electron withdrawing group. Now this is electron withdrawing by induction and resonance. This carboxylic acid, we have benzoic acid. So whenever we have any kind of a group that is an electron withdrawing group by induction and resonance, this is going to react slowly. It's deactivated, right? We're pulling away electron density. So it's deactivated. We need to heat it up to kind of try to speed up the reaction, but it's going to direct the reaction to occur at the meta position. This carboxylic acid group deactivating and meta directing. Very little ortho and para products. So let's look at why this is true. So for this would be any time where we have that polarized double or triple bond. Anytime we have that polarized double or triple bond, we're just applying it here to this carboxylic acid group, but we saw a whole list of other things that would fall into the same category, where if we add in our electrophile, we can add it to the ortho, meta, and para position. What happens? Well, we have this oxygen here that has a partial negative. And so it can pull away electron density toward itself, where we end up with a full negative charge. And the carbon that it's bonded to has a full positive charge. But notice here, that's going to have two positive charges right beside each other. So we get this separation of charge that is very unstable. Very unstable. Having two positive charges beside each other, very bad. You don't want to have two positive charges right beside one another. We get the same thing here, positive beside a positive, because this oxygen pulled away its electron density. And so we know that these are very poor contributors to the resonance form. But here, none of these are very poor. Yes, you can pull away electron density. If we did, we're still going to get a positive charge here on this carbon. But as we do that, it's not right beside. So look at where our positive charges can be. They can only be in these three places for this meta director. So the meta director knows that we get poor resonance contributors at the ortho and para position for it. Questions on that? All right, then our last category, this is the weird category. We have here a halogen that can withdraw electron density by induction, but that can also donate electron density by resonance. So don't think that these are the same as nitrogen and oxygen. They can do the same thing as nitrogen and oxygen, but what matters more for these is that they can pull away electron density, so they deactivate the benzene ring that they're attached to. They deactivate the benzene ring that they're attached to, yet they are ortho and para directors. So they're kind of doing two things. Usually we said something deactivated, it's going to be a meta director. Activated, ortho-para. But now it's deactivated and ortho-para because of inductive and resonance effects. Remember, these are electron withdrawing by induction and electron donating by resonance. So here we get mostly our ortho and para products. What's happening in the resonance forms? Well, we add in our electrophile. We can add it to the ortho, meta, or para position. We end up with this all octet form, strongly contributing resonance form, because yes, even though this is a partial negative, pulling away electron density by induction, it can at some point say, okay, fine, I do have a lone pair I can share with you. I'll help you out. So it can be generous. It doesn't want to be generous, but it can. And so it can donate in its electron density to help to stabilize that positive charge. So we end up with this all octet form. So the halogens are a special case. They're deactivators, yet they are ortho-para directors. So this is a table that you want to mark in your notes. It's very important. Increasing activation, you can see here that the strongest activator is going to be this aniline, where we have this NH2 attached to the benzene ring. That's going to work fastest, and remember, that's going to add to any open ortho and para positions. We can kind of temper that so it's less activated with adding in these groups on the nitrogen. And then we have our phenol and our alkoxy groups, so the ether, they are less activated than the nitrogens. We have our moderate and strong activators here. Then our weak activators are any alkyl or phenyl. What's phenyl? Benzene ring, right? And then we have our weak deactivators. So we were just talking about activators. They activate the benzene ring for this reaction to occur. Now we're looking at deactivators. So we have our weak and our strong deactivators. But notice that here, these weak deactivators fall in this ortho and para director box, whereas the other deactivators all are meta directors. The other deactivators are all meta directors. So here we have things that can pull away electron density by induction and resonance. Depending on what it is, and we've kind of talked about each of these. But we see that these are electron withdrawing by induction, but because of the lone pair, they are electron donating by resonance. Very important here. So make sure you mark this table because this will be important for the reactions we're doing. But here, what is happening? So they're saying if you have some kind of an R group on this benzene ring and you want to do the nitration. So what's nitration? NO3H2SO4. So we have and look at this bond. I'm going to draw this bond through a bond, NO2, meaning that this nitro can be added to the ortho, meta, or para position. The nitro can be added to the ortho, meta, and para position. I don't draw the bond to one of those. I'm drawing it through, which in organic chemistry means it could be bonded to any of these. So notice that for our ortho para directors, the ortho and the para products are going to be the major. Meta becomes major for our meta directors, but then for our halogens in the middle, even though they are deactivating, we're going to get mostly here our, sorry, I should just circle these, our ortho and our para products. All right, we'll pick this up on Wednesday. Have a good day, you guys. I'll see you in office hours, but I'll see you guys on Wednesday. Bye.
Thank you.
If you have questions, you can stick around.